What's in your lunchbox today?
All right, are there any questions about the homework at all? What? You got the homework? All right, I got to show you a few things that I didn't, maybe you already know. Discrete convolution is something that is more closely related to digital signal processing than continuous time convolution. We're working in that direction. Keep reminding yourself of that. So, I have to show you a few things about geometric sums. I didn't get to do this last time, I'm pretty sure. And I mentioned a few other things about systems in general. So, if you have a sum, this is a geometric sum, where I say from n goes from 0 to capital N of the function a of n. I'm going to keep this as simple as possible. I can make it very complex. Now this means you're going to be adding up all the numbers, a to the 0, which is 1, plus a squared, plus a cubed, all the way to the a to the n. Follow me? That's a geometric sum. I'm going to show you the trick to this because this will make you remember. If you want to know what that is, think this way. What if I have this? What does it really mean? It means a to the 0 plus a to the 1 squared plus dot 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 plus a to the n. It's a sum, right? The dot 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 just means it continues. It's a permutation. Well, if I look at that, I can say I'll take this a to the n, right here from n equals 0 to capital N. I'm going to multiply this by something. 1 minus a. I'm going to see what this looks like. Now, I want you to take a look at this. The 1 is just going to take all these terms and place them down here. So I'll have a to the 0 plus a to the 1 plus a squared plus dot 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 plus a to the n. I think everybody agrees with that, correct? Now, when I multiply this by a, it's effectively adding 1 to that exponent n. Do you all agree with that, class? With me? Can you all see it in the far back? Way back there. I wish I had your eyes. So this is going to be minus this same sum only with 1 added to every one of these. So it's going to be minus a to the 1 minus a squared, plus a squared plus a cubed dot 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 plus a to the n plus 1. Does everybody follow me on that? How many do right here? This is the trick. Now, let's examine this just for a second. If I look at a to the 0, there is no a to the 0 over here. Do you agree with that? What is a to the 0? 1. So 1 survives. I have a to the 1 here, but I'm subtracting off a to the 1, correct? You all see that? I have a squared here, but I'm subtracting off a squared, right? I'm subtracting off every single term except for a to the n plus 1 because it doesn't exist there. So I have to subtract a to the n plus 1 here. Are you with me? How many see this? Now by this time you see the trick. So now, I wish they wouldn't take these erasers off. I don't know who does that. But now what I can do is say if I take this and divide it by 1 minus a, you all see that is the sum. How many see that right there? Can everybody see that? And it's a simple, easy proof. And if you do any kind of, if you've worked in, I had one special topics in mathematics when I was an undergraduate. And one thing I learned with mathematics, if you're in advanced topics and stuff, you're always looking for some clever way to to get a result that is otherwise impossible to get. You're looking for tricks. I call them tricks. And that's a trick here. And there's a lot of them now. So what I can really say, this is the general, not general, but this is a basic form. You want to sum a series from 0 to n. That happens in discrete convolution all the time. I'm going to give you an example. Now, the more general form of this that I didn't show you is this. Write this down. And this you are required to know by heart. So listen. If I have a series and I want to sum up from n equals q1 to q2, a to the n, it's the same as this, but now I've replaced the lower bound. Instead of 0, it's q1. Follow me? This will be equal to a to the q1 minus a to the q2 plus 1 over 1 minus a. It's the same exact thing as that, only here, the very first term now will have a to the q1, where q1 would be the index you started on. Do you follow me in this class? Give me a show of hands if you do. And this is a very nice, easy way to do these things. How many remember this from your math courses? That was what, in your series? You had geometric series. Did you have binomial series? Do you remember that? Taylor series, expansions. What other ones? Maclaurin series? I'm trying to think of all of them. I remember doing all these. If you see the proof and the trick to it, it stays with you. If you don't, you usually forget it because you're trying to memorize formulas. That's the first thing I wanted to do. Are there any questions about this? Now, you should have run into this in your homework. There are a couple of problems that actually require this. Y'all with me? I'm going to give an example of this being used. But nobody had any questions about the homework, right?
I think there was one question. It wasn't the newest homework, but it was asking you to convolute u of t with the ramp of t minus 1, and I think it had the wrong solution to it.
All right. Let me do that one, but I first want to continue with the discrete convolution application of this. Do you remember seeing this used in one of the, there should have been used in a couple of problems. Do you remember this at all? No. How many did the homework? You don't, wasn't that used at all? Huh?
That wasn't.
Well, it will be now. Suppose I have a function, I'm going to convolve two functions. The first function that I have is x of n is equal to a to the n u of n. What could be more obvious? The second function I have is h of n is equal to u of n. But I'm picking a simple example so I can show you an application. All right, now of those two, which one has the most going on? The first one. The first one, right. So now I'm going to take that and just plot x of I here, right? And if I take a look at this, I basically have a to the, it's really going to be a to the 0, a to the 1, so forth, and it just keeps going down. It's really a to the I, all the way down if I look at this thing. And I can keep on, this would be, that's I, 2I, 3I, a to the 4I, and so forth. It just goes on and on. Do you agree with that? And it should be, I'm not showing it very well, but it should be asymptotically approaching 0. Do you agree? How many do? Now, let's just go ahead and take a look at this function. First, I flip it, right? And I get u to the minus I. U to the minus I, if this is I here, this is I here, it would look like this. With all these being 1, it would go on forever. And you can take, if you want to show the envelope, you can. How many agree with that? Now you'll notice right there, when I don't add any kind of value of n in there, there's only one point of overlap. That would be when n is 0. Do you all see it occurs only where I is 0, class? And the value would be 1. Now, if I go ahead and I say, when I add the index n plus, or excuse me, n minus I, effectively what I could do is do this, where this would be the nth value. Are you with me? I'm going to see this. Now you can see, and I chose a simple one, these are just 1. 1 times this, 1 times that, 1 times that. So really, the convolution would be the product of this times this summed, right, instead of integrating? And in fact, it would be the geometric sum, starting at 0 and going to n. You follow me? So this is a perfect example. My output, if I convolve these two functions, if I took y of n here as the convolution of x of n convolved with h of n, my h of n, this would be, I might as well just write it right here, this would be y of n equal to the summation of a to the I from I goes from 0 to n. And what is that value? Now normally I give you a number, I don't give you a, it could be a half, it could be a quarter, something like that. But what is the value going to be? Well, what's on top? Does anybody remember? 1 minus, remember the lower bound 0, so it's a to the 0 is 1, right? Minus a to the, very good, n plus 1 over 1 minus a. And that is the convolution. It's a very simple, it's almost the exact application with no modification of the geometric series. Now, let me tell you how this usually unfolds. The next permutation is, let's not do this u of n. Let's do something where I have u of n minus u of n minus 3. What does that look like? First, what does that look like? Well, it's 0 for all time except from n equals what? 0, 1, and 2. Not 3, because at 3, the second one turns on and cancels it. Follow me? So if I was to plot this function, just so you have a record of it right here, it would look like this. This would be versus n, or versus I. This would be at minus 1. At 0, it would go to 1. At 1, it would be 1. And at 2, it would be 1. But then it would be 0 from there on. 3, 4, and 5. Follow me in this class? How many see this right here? Y'all with me? Now, if we're convolving that, the top part I'm going to state, I'm saying we're going to use this x of n, but now this is the function I'm convolving it against. So now we have to flip that one and shift that one. Are you with me? Everybody? Show me show of hands here. How many see this? I'm going to erase this. It's a little sloppy to begin with. Now when I do that, I'm going to start with just this, only minus I, which takes this and flips it that way and replaces n with I. Do you all agree with me, class? Show of hands so I know. All right? So now I'm going to take, this is I, this is 0, this is 1. Oh, better than that. This is 1, this is minus 1, minus 2, minus 3. So right at 0, here I'm going to have h of minus I. It looks like this. There's 3 values that are non-zero. All the rest are 0, correct? I haven't added any value of n other than 0 to the minus I argument inside of h. Correct, class? You'll notice that's the point where it overlaps. And remember what's happening here. When I put n in here, for n greater than or equal to 0, this thing starts marching this way. Got it, class? How many see this? All right, do this one with me. I'm trying to keep this in a way where I don't make too many changes so you can see it. So now, in general, what you can see is, and there's a couple of domains, for n greater than or equal to 0, less than or equal to 2, what happens? And the reason I did that is now I'm going to go ahead and put the operation n minus I here. And while I'm at it, I assume you know this, but I better show you this. When I talk about discrete time convolution, what I'm talking about is sum, right, of I equals, really technically minus infinity to infinity, right, of x of I times h of n minus I. But really, we know we're not going to start here because unless there's overlap, it makes no sense. 0 times something is still 0. So we always only look at the region where both functions are non-zero. Do you follow me in that, class? That's the formal definition. This one, in our case, is going to start at 0. All right, and it's going to go to n for that first part. So when I look at this, this is when n is 0. When n equals 1, I shift it here. when n equals 2, I shifted here, correct, class? Well, that's still only the front edge is changing its value. The back edge the overlap starts at 0. But once I'm past 2, now I've got to start doing a different sum. How many see that? All right, what's this sum going to be for y? This is y then for this condition. It would be the sum of what? A to the I from I goes from where to where, people? 0 to n, right? And n's limited to be either 0, 1, or 2. No other numbers. You all agree with that? And what's that value going to be? That's going to be 1 minus a to the n plus 1 over 1 minus a. But that's the condition where it's valid. N greater than 0, less than 2. Everybody see? Agree, class? Now, and I'll take it from the audience, what happens when n is greater than 2? And by the way, I didn't say this, but for n less than 0, y then the convolution is 0. Do we agree with that, class? Without me stating it too many times. Agreed? So what's this one going to be? Well, now, when I look at that, when n is greater than 2, I can erase this easy. I know you probably hate me for that, but it makes my life easier. It saves time. I can erase this and do this and say, well, now we have 0, 1, 2, 3, 4, and so forth. But now, when it's greater than 2, y'all agree with that? Right? And where does it start? Where does it stop? Well, before, when it was from here to here, it was n equals 0. N equal 1, right? N equal 2 is direct overlap, right? Now here, for n equal greater than 2, it's going to start at what? This would be n equal 3. It's going to go from n minus 2. Say it? 3, isn't it? Think about it. Well, let's see. Let me do it again, just to show you. If I take a look at this, actually 2, you're right. Whoever said 2 is right. If this is 2, this is going to be n minus 2, right? If this is n equal 2, this is n minus 2. I'm sorry, you were right. Whoever said 2 is correct. So now we're going to say y then is equal to the sum of a to the I, and it would go from I equals n minus 2, because you count 0, remember, to what? N. Correct, class? How many agree with that? You all see what I'm doing here? Now what's that sum going to be? That's my real goal.
2 to the n minus 2 minus a to the n.
Right.
Minus
A to the n minus 2 minus a to the what?
n.
Plus 1. Right? You have to add 1 to that. Do you remember? All right. Divided by 1 minus a. And then, now you see this. And by the way, that will asymptotically go to 0 for large values of n. This one will. Because what's happening is the window is shifting through here, and this thing is monotonically going to 0. Are you with me on this, class? And we could go through a lot more permutations of that, but that's an application of using the geometric series, the two very obvious and interesting types of sums. Okay? Yes, sir?
Would the second equation work for the whole range instead of just 2 to infinity?
Well, now I want you to think about this. What about when n is 1? 1 minus 2, it starts at minus 1, and you don't have an a to the minus 1, right? It's 0. The overlap would be 0 times that, so it wouldn't.
If it's just 0 at the minus.
I'll tell you how you can make it work. If you want to know what you do to make it work, you put u of I in there. Then it works. All right? But I don't want to do it. All right? All right. Now, you had a question. No, didn't you ask me about some problem and had the wrong answer?
Oh, it was asking you like graphically convolute u of t and the equivalent of r of t minus 1.
All right.
Except I think it had like u of t minus 1 squared over 2.
Let me take a look at it. Anybody know what this weekend's weather is going to be?
Rainy and cold.
Hmm?
Sunday's gonna be
Rainy and cold.
Looks like I'm not going boats.
I know, I'd rather do that option.
All right. describe the problem.
It was U of T convoluted with, I mean, it's T minus 1, U of T minus 1, but
Wait.
T minus
T
1.
minus 1 convolve times U of T minus 1?
Yes. And then it was convolved with a U of T.
What?
It was convolved with a U of T.
Alright, now, if you're going to do this problem, this is me speaking now. This is the one to me has the most stuff going on, so I'm not going to flip that one. With me? So I leave that guy alone, and I plot it versus not T, but tau or lambda, whichever one you want. Tau in our book, isn't it tau?
In the book, it's lambda.
Lambda, it's lambda. Whatever, it's the dummy variable. So if we're plotting, is it lambda in our book for real?
It changes something.
It goes back and forth.
It goes back and forth.
What- I don't care. I think he uses tau more often, but let's use tau for that. So if we do this, we're going to plot that first one, tau minus 1 times U of tau minus 1, which starts at 1. Now remember, that's tau. And it looks like this, with a slope of 1. Do you all agree with that? The equation for this line, for greater than 1, is simply going to be equal to tau minus 1. That is this slope, and that would be my, I'll call it my x of t, or x of tau in this case. That's what it is, just tau minus 1. Do you all agree? This is for greater than 1. Now, I take this one, U of t, and I flip it. And when I flip it, I see I get this, U of minus tau first, and that looks like this. Height 1, this is versus tau, right? Agree, class?
Mm-hmm.
Now, when I add t inside here, let me do it this way. Now I'm pulling the curtain to the point where t is right here. I call it pulling the curtain. Y'all agree with me? Now, until t equals 1 or is greater than 1, there is no overlap between the bottom and top functions. Do you agree with me? So now you can say, just by inspection, once t is greater than 1, this would be the overlap. Agree? So when we take a look at this, and please watch this, I can say, therefore, my y of t will be 0. The convolution of those two, I'm going to call y of t. I usually do this. Will be 0 for t less than 1. And then y of t will be equal to the integral from 1 to t, right, of, it's going to be tau minus 1 d tau for t greater than or equal to 1. Do you all agree with that, class? I don't know. Do you remember this problem, people? Yeah. All right. Well, if you do this, you get the integral of tau is tau squared over 2. The integral of d tau minus d tau integrated is tau. Then you evaluate this from 1 to t. I'm just putting in the values. Do you agree? And from here, what do you get? This is tau is going from there. I get the quantity 1/2 minus 1 minus the quantity, or sorry, I'm doing it the wrong way. It's going to be equal to t squared over 2 minus t minus the quantity 1/2 minus 1. And I'm just literally putting in the values there. And if you look at this, let's see, what do you get? Well, I got 1/2 minus 1 is minus 1/2, with a minus sign is plus 1/2, right? So I know I have a half there. And then I have plus t squared over 2 and minus t. And that should be the answer for t greater than. Is that right?
So my real question was, so the answer key listed is U of t times t minus 1 squared.
Oh, what they're doing is they don't want to, they're going to have this whole thing here times U of t
Well,
minus.
no, but, my question was, shouldn't it be U of t minus 1? That you don't have non-zero values before 1?
There's a trick you can do where you can, well,
They used the wrong U of t.
maybe they did. Don't worry about it. That's the right way to do it. And listen, unless you have to use U of t's, don't. Just put domains.
All right.
All right? That's the way it's normally done anyway. Oh, all right, class? I got a few other things to cover today. I mean, I have a lot of things to cover, but I won't get to all of them. I want to talk to you about, the next thing I'm going to talk to you about is something that's really, really important that I think I mentioned briefly, but I'm going to mention again. And it's causality. Now this is something that I'm going to just spend a few minutes talking about. It will make perfect sense to you. The word is causality. It implies something, an event here, causes something here. It causes it. Understand? Now, when we talk about whether you have a causal or non-causal system, here's the key. If I have an event, let me use a delta function. Suppose this is my system. It's defined by h of t. And I put my input as x of t equals delta t. That occurs at t equals 0. If we looked at where that occurred, if this is t and this is x of t, it would be just a delta function at 0 if this was t going out here. Do you all agree? That's the input. The output h of t here could be anything. In this case, my y of t would be the convolution of this times. But let me just put h of t down here. I won't even put y of t because it's an impulse. I'll just say this is h of t. Well, if h of t looks like this, if this is 0 and this is time, and this is h of t, if it did something like this, like so, it started 1. If it started at 1 here, follow me. You could say that this event started at, this occurred at 0, this started later than that. It makes sense, that's a possibility. Do you agree with that? Now keep watching. But what if this output occurred and the input was this? Not delta t. Let's say I got that input, but for delta of t minus 2. Well, that means 1, 2. Now the delta function right here, delta of t minus 2, it starts at 2, correct? Remember, that's my input. So there's no input at 1. Got me? No input until we hit 2. It's all 0. But this thing somehow anticipated that there would be an input. That's non-causal. That's not a system that is really possible in real-time processing. Follow me on this, you're going to see it. This should be obvious to you. It's like, why are we even talking about this? It makes no sense to me that you would even think of a non-causal system, but you're going to see, in fact, that some of the functional forms we'll be dealing with later on in the frequency domain render things that are non-causal in the time domain. I'm only telling you this to prep you for what's coming. However, listen carefully. This type of a system response, input, output, like that, where the output anticipated the input coming at 2, would be allowable and useful if we had not a real-time event that was going on as in real time, as I'm speaking. But if we had a strip recording, suppose I recorded something for 2 days. Now I have a data record. Now I could use any type of h of t, be it causal or non-causal, to process that data. Does that make sense? Because now I know all the values for all time. And then that system, you could use non-causal processing type things for that. But you can't use them in real time, which is most of the stuff we do. Yes, sir?
So hypothetically, if that input never occurred, would the h of t still be there?
What's that?
If that input never occurred, would the h of t still be there?
No, because it's the impulse response. No impulse, no response. It's like, if this is 0, then that's 0. Because one thing about systems, any kind of we're still using linear system. Any linear system can't have an output unless you have an input. And I take it back, if there's a steady state DC output, that's allowed. All right, that's called a DC offset. I don't want to spend too much time on this because we can go down, and you ever had a philosophy course, you can really get yourself buried in sort of these abstract things that never can happen. But that's a real thing I want to talk about. The next thing I want to talk about is bounded input, bounded output. Now, and then I'm going to tell you the condition. These are just things that I'm telling you because they're terminologies you have to be familiar with. Bounded input, bounded output, bounded input, bounded output. But it's in the book. Simply stated, it means this. If you have a system, a linear system, linear time invariant system, better watch out what I say, and I have some x of t, and x of t is bounded. It's not going to infinity. It's something bounded. Then your output would be bounded. It means it will not be infinite. Follow me? It will not tend to infinity. It's going to be bounded. Now that's what we like. We don't like unbounded systems, but there are unbounded systems out there that are actually useful. So what is the condition for this? Your book doesn't give a lot of examples of some that are, that some that not. They have a few. But the condition that it is bounded input, bounded output is this, that the integral of the magnitude of h of t, remember it's the magnitude, so if h of t was a sine of omega t times e to the minus jt or something like that, you'd have to take the magnitude. It's all positive. Got me on this class? And you get rid of any imaginary terms. If you take h of t and you integrate it, take the magnitude of h of t, the impulse response, from minus infinity to infinity, it has to be finite. It has to be less than infinity. That is the definition of a bounded input, bounded output system. How many have heard that term before? Don't you use it in computer systems sometimes at all? What?
I mean, computer system right now.
Did you use it?
No.
All right. Well, you're going to hear a lot. That term is common with a lot of the stuff that you run into in engineering. In radar, we always talk about something like these kind of terms. So those are the two things I wanted to cover, and I was going to start my way down into Laplace transform. The only thing I'm going to do today, don't look all like I hate you, not yet. I'm going to do you a favor. How many have had Laplace transforms? Every hand should be up here if you have the prereqs, unless your teacher died or something, because you were supposed to cover this. The Laplace transform is, of all things, the easiest of the transforms. And the reason is because the integrations are always usually doable. This is the definition of a one-sided Laplace transform. It's simply this. If you have an f of t, it will render an f of s, where s is now going to be the variable, transform variable. And it says that this relationship is gotten by saying f of s is equal to the integral from 0. Remember, it starts at 0, not at minus infinity, unlike the Fourier transform. And it goes to infinity of f of t times e to the minus st dt. Now, I have to say one thing. I know you've had it, but I'm going to go ahead and restate the obvious. S is a complex number. In general, S has a real part that is labeled sigma. It is not the conductivity. It's simply the real part of this complex frequency S plus j omega. This j omega here is the omega you can think of in your circuits courses that was 2 pi f. That is the omega. Understand, class? And I'll spend more time on it. Think of that. That's a real frequency, a radian frequency. Now, when you do this operation, first you have to get familiar with doing it. I'm going to do it for maybe 2, 3 functions maybe, okay? Just simple ones to get a start because you're going to get some homework on this. That's the reason I'm going to do it, and then you get your quiz, all right? Just work with me, guys. So let's suppose that I have a really simple function. By the way, can somebody tell me what advantages of the Laplace transform, one clear advantage of the Laplace transform that you see based on what you've had so far? Anybody? There's one thing that should pop up. What?
Advantage compared to what?
Everything else. All right, I'm thinking, maybe I didn't phrase it quite. You remember in differential equations? How many remember the integration factor? How many remember being like pulling your hair out when you had second order differential equations that were not homogeneous trying to find the integration factor? If you don't even know what I'm talking about, then don't worry about it. But Laplace transforms allowed you to take the Laplace transform of that. Instead of solving differential equations, you solve what? Algebraic equations to solve it. Do y'all remember that? That's the strength of the Laplace transform that you should know. So let's go through some functions. You can use x of t or f of t, either one. I'll use x of t here. Suppose the first one is, here's x of t, and here's the Laplace transform of it. I'll go through the properties next time. Suppose I do a simple one. X of t is delta of t minus, say, a. What is this going to be? Well, evaluate this and think of the basic definition. If I take the integral from 0 to infinity of delta of t minus a times e to the minus st dt, what did I tell you about what a delta function does? Where do we care about? What time do we care about here in this integral? When t equals, and what do? We find out what's next to it and stick in a for t and pull that out. So that's simply e to the minus sa, and that's it. And that's the Laplace transform of delta function using the fundamental definition. What happens when a is 0? Come on. It's 1, which is real important. The transform of a delta function in the Laplace domain is 1. That's real important. All right, next, we could do this a lot of different ways. Suppose I had the function, this is the last one. If I had e to the minus at u of t, and you wanted the Laplace transform of that. I'm going to erase this one. I bet you all know this one. This would be the integral from 0 to infinity of e to the minus, and since there's an a there, now watch what I'm doing, a minus a, I'm just going to put as minus a plus st in here dt. I'm simply combining, because this is e to the minus at, e to the minus at times e to the minus st is e to the minus a plus st. Do y'all agree with that? And that is simply going to be equal to 1 over a plus s. And here I stop. 1 over a plus s. And we'll go down and we're going to build a table that you will be responsible for knowing. They're the basic functional forms. And then we'll use something called the properties that I'll prove to get all the other ones. Come on down. And now we're going to take our quiz. What I'd like you to do is try your best to space yourself with one empty desk. I don't know if it's possible, but do your best. Take everything off your desk. Take your phones and put them on the desk upside down. And I'll ask everybody as I'm coming around to stand up. Just follow me on this. Let me show you how we do this.